All right, so we are at the last part of the section on concurrency, and this is the part on concurrency bugs. So read the chapter in the middle section on concurrency, and the one that we're looking at right now is towards the end. It's called concurrency bugs. So remember, we are in the part of the course that deals with concurrency. We're at the very end pretty much of this part of the course, and then we'll move on next to persistence after this chapter. Let's do a quick review of locks, condition variables, and semaphores. So we saw that multi-threading is really good. It's a really good thing to have. However, it can give you unpredictable results. The main reason being that the scheduler of the operating system cannot be predicted easily. So it's unpredictable, and so you can't always expect to know the order. Also, you have critical sections that we have to control access to, and one way to do that is with locks. Or you can also use semaphores, but locks are the usual way of doing things. And we also saw that you can have problems. You can lock things incorrectly, like we saw in the previous lecture. If you have the producer-consumer problem with semaphores, you can have the situation where two threads are waiting for each other and they wait forever, and that's called deadlock. It's also interesting to note that you can inadvertently set up a deadlock situation just by forgetting to unlock. That's very simple and very easy to do, but you don't want this in your code. So you can have, as a result of programmer error, you can get deadlock in your code. So there was a great study, an in-depth study of concurrency bugs in 2008 by this author Liu. This is referenced in the Operating Systems 3 Easy Pieces, chapter 32. And what they found was very interesting. Out of a total of more than 100 bugs, more than two-thirds were actually not deadlock, while about a third of the bugs that they found were deadlock. So they looked at the source code from various open source projects. So that's the nice thing about open source, is you can look at the source code and find bugs, things like that. And so they looked at like 4 very different applications. MySQL is a database server, Apache is a web server, Mozilla is the code for Firefox, things like that. That's a web browser, multi-threaded. And then OpenOffice, or we tend to use the next sort of version of this called LibreOffice. And so LibreOffice is maybe something you might be familiar with. That came from OpenOffice. And that was an office suite. That's sort of like a Word, Excel, sort of the free version of that. Okay, so the bottom line is, once again, is that there are a lot of deadlock bugs, but not all concurrency bugs are deadlock ones. There's actually twice as many that are not. So the crux of the problem is, how do you handle some of these common concurrency bugs? How do you recognize them? Turns out there's like 3 main types: atomicity violation ones, order violation, and then deadlock. And then deadlock, once again, is where you have code that seems to run, but then you end up with a whole bunch of threads stuck. And so we look at strategies for fixing them or just plain avoiding them. How do you avoid getting into these buggy situations in the first place? Okay, so let's take a look at some of them. Examples. So atomicity violation we've actually seen before. And so this is a situation where you have 2 threads and they both try to access a variable, and then one of them is writing. In this case, let's say thread 2 is going to set this thread arrow proc info to null, but then thread 1 assumes that it has checked to make sure that it is not null. And so this if statement, what it does is check if it is not null. If it is not null, then it executes this code, which presumably will rely on the fact that thread arrow proc info is not null, and sure enough, here it is. You try to write something into a file or someplace like that, and this assumes that thread arrow proc info is not null, and assumption is that if it were somehow to become null between this point and this point, then this would fail and maybe the whole program would crash. So once again, thread 1 checks if something is not null, but before it has a chance to use that information that it's not null, thread 2 gets in there and sets that very same thing to null, and so then something in here in thread 1 will fail. So we've seen this before. This is actually, and this is an example from the MySQL database server. So it's really interesting to see. So the definition is that you desire some serializability among these multiple memory accesses, but that's violated. There's a code region that is supposed to be atomic, but that atomicity is not enforced during execution, and we've seen how to fix this. Use a lock. So this is how you would set this up. You set up a lock in the shared process address space for the two threads, probably in a parent address space. We declare a lock and initialize it, and then in both threads we have to lock. So here it is in thread 1, you lock, and thread 2 also does a lock. So only one of them will get to do its critical section. So thread 1 says, okay, I'm going to check if this is not null, and if it's not null, I will do this. Since you locked it, sure, everything in here should work, unlike the previous case when you didn't have the lock. So as long as you lock it, you know that thread 2 cannot come in there, and if it tries to execute, it'll have to wait for this unlock before it can go ahead and change this thread arrow proc info to null. So this takes care of the problem. And if you reverse the order, like if you thread 2 actually goes first, all it will do is set it equal to null and then unlock, and then even if thread 1 is waiting while thread 2 was setting this to null, it'll just wait here, and then once thread 2 unlocks, it will be able to lock. It will check the value, it'll see the null, and it'll say, oh, I can't do this, and so it'll just go to the statement after the if statement, which is the unlock. So no problems, since in this case we don't even execute this code. Okay, let's take a look at another problem, that is order violation. So here we have once again two threads executing different code, and so in one code you are asking to create a thread which will execute, let's say, this mmain function, and then in mmain you are going to dereference this variable which is going to be returned by this call. So the bottom line is that you're trying to set this here, but we're trying to use it over here. So if thread 2 execute this mmain method or function before thread 1 now executes its code to set the same variable mthread, then this dereferencing will cause this thread 2 to crash and maybe the whole program to crash. So we've seen this kind of thing before. We definitely want to execute this only after this is done. Okay, so some desired order between two groups of memory accesses may not work, and let's say some chunk of code A should always be executed before B, but we're not enforcing the order, and so one way to fix that, or one way to enforce the order, is to use a condition variable. Okay, so let's take a quick look at that. So here's how we use condition variables. This should all be review from previous chapters. So we set up condition variable, and then remember that As soon as we start to use a condition variable, we find out that we also need a lock. And here's the actual int that we're trying to protect. So here is the code again. The old code just had this. You're setting mthread using the return value of this function. And so we're setting the value of mthread. We only want to use mthread in thread 2 after thread 1 has done its part. So I'm guessing this sounds familiar. Thread 2 wants to execute some code only after thread 1 has finished its step. And so here it is. Here's that step. Once you're done with it, then it can signal to thread 2 that, okay, I'm done. Go ahead and do your stuff. And so way to do that is to use condition variables. And so here is that chunk of code. You lock, you set that minute to 1, signaling that you're done, and then thread 2 can go ahead, and then you actually call the signal functions. Remember, this is all shorthand, and then you unlock. On the other hand, in thread 2, you have to wait for that signal. So to wait for that signal, remember, you have to lock. And then here's the tricky part again. When you do the wait, you have to pass in a pointer to the condition variable and the lock that you're using. Because remember, you're going to unlock in here and then let whatever thread is trying to lock it. And then when this unlocks, this wakes up, or when you signal and unlock, this wakes up, and then it actually locks again, checks the while loop, gets out of this, and then unlocks one last time, and then everything is unlocked. So this should all just be reviewed, but the basic idea is that you do a step, you tell the other thread, okay, I'm done, and then thread 2, which is waiting here using this condition variable, waits for that signal, and then it goes ahead and executes this code. Okay.